everyone. In this video, we are going to cover the MCQs question on the topic complementary graphs, Euler path in Euler circuit, and Hamilton path in circuit. Starting with the first question, if a simple graph G contains n vertices and m edges, then the number of edges in a complementary graph is equal to what? The concept is very simple. If we have any graph G, we need to construct the complementary graph. Make sure the count of vertices in both the graphs are same. Means if the number of vertices in a graph G is equal to n, and that is also is equal to the number of vertices in a complementary graph. Secondly, how to construct the complementary graph? As per the definition, whatever the edges is not present in a graph G, that we will include in a complementary graph. Let's take an example with the 4 vertices. Suppose we have this graph as a G. Now what is a complementary graph in this case? First, the count of vertices is same, so we will take the placing of the vertices as placed in a graph G as it is. Now, this vertex is connected with the second one, but not with the fourth and third. So we can take these edges in this case. Whereas the second vertex is connected with the first and the fourth, but not with the third. So we can connect with the third in the complementary graph. Third is not connected with any of the vertex. So make sure it is connected with all the vertices in a complementary graph. Fourth is not connected with the first and third, and it is already connected here. So this is how we take the complementary graph. Remember that complementary graph is defined for the simple graph. Simple graph means no multiple edges, no self-loop. And remember that when we take the union of these two graphs, that always give you the complete graph with the n vertices. In this case, we will get a K4. With the help of this result, we can calculate the number of edges in a complementary graph. According to this, the number of edges in a G graph plus number of edges in a complementary graph is equal to number of edges in a complete graph with n vertices. Now, as per the question, total number of edges in a graph G is m. Number of edges in G complementary graph, we need to calculate that. That is represented by G bar. Now, how many edges we have in a complete graph? In this case, we have n into n minus 1 by 2. Simplify this. So, number of edges in a complementary graph is equal to n into n minus 1 by 2 minus m. Further simplify this. This is n square minus n. Here we can take the LCM. We get minus 2m by 2. According to this, option A is correct. We have this general procedure to evaluate the number of edges. We can also answer this with the help of example. Like in this case, total number of edges in a G graph is 2. So here we can take the m is equal to 2. Total number of vertices, that is represented by n, and that is 4. How many edges we have in a G complementary graph? So here we have 1, 2, 3, 4. With this data, find the number of edges of a complementary graph that must be is equal to 4 from these 4 cases. According to the first case, it is a n square, that is a 16 minus 4 minus 2 times of 2 by 2. Is this is true? 16 minus 4 into 4, 8, that is equal to 4. Is that is applicable in the second case? Clearly not. Similarly, check for the C and D. Now the question is how to remember how many edges are there in a complete graph in a journal format. If we have a complete graph, we will take any one example, suppose K4. Calculate the degree of each vertex, that is 3, 3, 3, 3. As per this, the degree of each vertex is 3, and here we have taken the K4 graph. And if I take Kn graph, degree of each vertex is n minus 1. How many vertices we have? That is the n. So total degree is represented by this form, that is n into n minus 1. And by hand checking theorem, you will get this result. Let's take another example. If G is a simple graph with 6 vertices and 9 edges, then how many edges the complementary graph G have? The same concept is applicable. We will use this result. The number of edges in a graph G is 9. We need to calculate the number of edges in a G complementary graph and total number of edges in a Kn graph, where n is 6. So we can directly plug the value of n as a 6, that is 6 into 6 minus 1 by 2. Simplify this. This is equal to 9 plus number of edges in a complementary graph, that is equal to 3 into 5, that is 15. From here, number of edges in a G complementary graph is equal to 15 minus 9, that is 6. Hence, option A is correct. Next question we have a simple graph G with the 7 vertices and its complementary has a 13 edges. Then how many edges the graph G have? In the previous case, we have evaluated the number of edges in a complementary graph. Now we need to evaluate the number of edges in a G graph. We know the result, number of edges in a G graph plus number of edges in a complementary graph, that is equal to number of edges in a complete graph Kn, that is equal to n into n minus 1 by 2. Total number of edges in a complementary graph is given as a 13. So here we write 13. We need to evaluate this, keep it as it is. Now what is the n in this case? That is the number of vertices. Now number of vertices for the graph G is given to us. So remember that number of vertices for the G graph and its complementary is same. It means here n is 7. So 7 into 7 minus 1 by 2. Simplify this. So number of edges in a G graph is equal to 7 into 6 by 2, that is 7 into 3, 21 minus 13, and that is further is equal to 8. Hence, option A is correct. Next question we have, if we have the G as a simple graph with the 10 vertices and it is a complete graph, what is the count of number of edges in a complementary graph? As per this, what we have, number of vertices in a graph G, that is 10. Next data is available as a complete graph. If it is a complete graph and we know the total number of vertices, we can easily evaluate the number of edges in a graph G. That is equal to n into n minus 1 by 2. This is equal to 10 into 9 by 2. That is equal to 45. Now the question is, how many edges in a complementary G graph have? As per this, the data is number of edges in a graph G plus number of edges in a complementary graph is equal to the number of edges in a complete graph K. As per this, the value of edges in a graph G is 45 plus number of edges in a complete graph is as it is, that is equal to number of edges in a complete graph Kn. N is 10, again it is a 45. So as per this equation, we are getting the number of edges is equal to 0. Next, which of the following finds the length of shortest path between two vertices in a connected simple weighted graph? Direct result we have, that is called as a Dijkstra's algorithm, whereas Descartes and Ohm's theorem is applicable in the concept of a Hamilton circuit. Let's take another example. Consider a connected undirected graph with 8 vertices. If exactly 2 vertices have a odd degree, which of the following statement is true? As per the option, we need to comment on the Euler circuit and Euler path. Now what does it mean? Euler circuit means we need to find a path that covers every edge exactly once and end point of path is same. Whereas Euler path means we need to find a path that covers every edge exactly once, but the end points are different. We can also predict Euler path and Euler circuit in a graph without its virtual representation. How? For that we need to know about the degree of each vertex. If the degree of each vertex is even, then definitely that graph has a Euler circuit, and exactly two vertices are there of the odd degree, then in that case it has an Euler path. Now, how to remember these results? We can remember this with the help of example. Suppose we take a cycle. Can you cover each and every edge exactly once? Or we can say that, can you reconstruct this graph without lifting pen? Yes, we can reconstruct that, and we have reached at the same point where we have started. It means it has an Euler circuit. Now relate with the help of degree. Degree of this vertex is 2, 2, 2, 2. Degree of each vertex is 2. It means it has an Euler circuit. Now if I take the same graph, rather than this, if I add a diagonal here, exactly two vertices are there whose degree is odd. Now whether it has an Euler path? Yes. Can you cover each and every edge without lifting pen? And the end points are different. Yes. How? We can take an edge first this, then this, move to the first one, then fourth, then the third. As we have started from the first, now we are ending at the third. End points are different and we have covered each and every edge exactly once, so it has an Euler path. Now read the statement. 8 vertices given to us, exactly 2 vertices of the odd degree. If we have exactly 2 vertices of odd degree, it means the graph has an Euler path, not Euler circuit. Hence option C is correct. Next, a connected graph has exactly 4 vertices of odd degree. Which of the following is true? Now we have 4 vertices. Degree of each vertex is odd. Whether it has an Euler path? No, because in the case of Euler path, we need only 2 vertices of odd degree. For the Euler circuit, the condition is degree of each vertex is even rather than odd. It means neither it has an Euler path nor an Euler circuit. Hence option C is correct. Next, in a simple undirected connected graph with n vertices, m edges, what is the maximum possible number of vertices with the odd degree such that graphs still contain an Euler path? It means again we need to deal with the same condition. If the graph has an Euler path, exactly two vertices are there of the odd degree. Hence option B is correct. Which of the following statement is always true for any connected undirected graph? The sum of the degree of all vertices is even. If the statement is true, what does it mean? If we take the summation of degree of all vertices, it say that that is always even. Yes, the statement is true. How? Because that is equal to 2 times of number of edges by the handshaking theorem. Hence option A is correct. Let's check it whether B, C or D is correct or incorrect. Every connected graph has an Euler circuit. No, because if exactly two vertices are there of the odd degree, it has an Euler path, not Euler circuit. Or we can take the example of this. Degree of each vertex is 1 and it does not contain a Euler circuit. We can cover each and every edge exactly once, but the end points are not same. Like in this case, if you try to construct a path whose end points are same, A, B, then move to the A. In this case, this edge is repeated twice, but we need to cover it as a once. It means clearly this is incorrect. Next option, if a graph has a more than 2 degree vertices, then it has an Euler path. Clearly incorrect because we said exactly 2 vertices, not more than. Next, A graph with all the vertices of even degree is disconnected. No. If I take this graph, cycle, this one is connected. So hence D is also incorrect. Next question, a Hamilton path in a graph is what? Now we are going to deal with the concept of Hamilton path and the Hamilton circuit. Hamilton path means we have a path that cover each and every vertex exactly once. Whereas in a Euler path, we cover each and every edge exactly once. But the endpoints are different. Same concept is applicable in the case of Hamilton path, but we cover each and every vertex. Whereas Hamilton circuit means we need to cover each and every vertex exactly once, but the endpoints are same. So in path, we need to cover every vertex exactly once. For example, in this case, we need to cover each and every vertex exactly once. So we can cover by this form. So there is no need to cover each and every edge exactly once. Statement is cover each and every vertex exactly once. And if we can reach to back to this one, it means it contains a Hamilton circuit. So in this graph, it has a Hamilton path as well as Hamilton circuit. Taking the next case, which of the following is true about the Hamilton circuit? Every connected graph has a Hamilton circuit. We can't say this because in this case, this graph does not have a Hamilton circuit. How? We can start from the vertex A, we can move to the vertex B, then C, then D. Now we cannot come back to the A. Or you can start from anywhere, you will not get a Hamilton circuit. So remember that if a graph has a pendant vertex, means the degree of a vertex is 1, clearly that graph has a no Hamilton circuit. So this statement is incorrect. Next is, if a graph has a Hamilton circuit, it must be complete. It's not necessary. Let's take this case. C4. It is not a complete graph because we have not taken the diagonal edges. Although it contains a Hamilton circuit. So again B option is incorrect. C option, a graph can have a Hamilton circuit without being complete. Yes, like in this case, it has a Hamilton circuit. It is not saying that for every graph can have. Yes, it can have. So it means the statement is true. The next one is no graph with a vertex of degree less than 3 can have a Hamilton circuit. No, clearly incorrect with the help of this example. Degree of each vertex is 2, that is less than 3, but it has a Hamilton circuit. So it means D option is also incorrect. Taking the next case, which of the following graph definitely has a Hamilton circuit? A tree with more than 2 vertices. Let's take a tree as this. Does it has a Hamilton circuit? No. We can start a path from any vertex, but we cannot end at the same vertex. Because either we can start from A, then move to the B, then C. From C to A, there is a no edge. It means it has a no Hamilton circuit. And also I have informed to you, if the degree of any vertex is 1, then it has no Hamilton circuit. So in tree, we have the leaves and the degree of each leaf is 1. So clearly A option is incorrect. A complete graph with n greater than equal to 3 vertices. Definite has a Hamilton circuit? Yes. We can take the outer boundaries. Every time you will get a cycle form at the outer boundary and clearly it contains a Hamilton circuit.